Okay, let's get started. So welcome everybody to the class seminar. Today we have Allison Lowndes from NVIDIA. Allison is a deep learning solution architect there, and today she will be sharing advancements about artificial intelligence, and I will let her introduce herself a little bit also.
Ground rules.
Ground rules. So if you have questions during Allison's talk, please use the chat box. Any other ground rules?
And there will be time after the presentation for questions.
Specifically dedicated.
Okay, wonderful. So I'll kick off. I'm going to do a quick hi and then switch webcam off, simply because I'm currently in a hotel room in Switzerland, and I'm not entirely sure what what kind of behaviour I'll get from the internet connection. So bear with me 1 second. Okay, so this is me. I've been with NVIDIA for about 4 years now, and for the first 18 months I was as a deep learning solutions architect and also community manager, so the community of AI researchers. I've now been given a much wider role, which is artificial intelligence DevRel, so developer relations. And I'll go through a few of the things that I actually do with NVIDIA. So to begin with, we do a lot of national level training. We actually have two separate programs. One is called NVIDIA, which is NVIDIA AI Labs, and that is 25 now of the world's top AI labs that we work very closely with, particular PIs, etc. But we also have NVIDIA AI Tech Centers, where we work very closely with universities, and Florida might be interested in doing that with us. Where it could be industry focused or otherwise. But this was born from an original program, which was the Centers of Excellence. And so we actually do a lot where, obviously we are industry, but we have a very large research arm. So we can put together state-of-the-art AI computing and our general platform, along with the actual applications of deployed or applied AI. And at the same time, we do a lot of training, both at industry level, but also, as I said, at the national level. So, I've personally trained members of the UK Parliament, the UK, as well as a lot of the European countries, all started rallying together a couple of years ago now about their national AI strategies. And of course, that also comes down to the industry solutions, which affects everyone. So we have a lot of work that goes on continually in not just, as it says here, transportation, healthcare, smart cities, and manufacturing. They're just some examples, but it's really across the board. If you can think of any kind of deployment of potential AI, no matter how minor, we're involved with it. One of the first things that I did back in 2016 was met a gentleman called James Parr, and he's responsible director of something called the Frontier Development Lab. So he had this great idea that because he was currently contracting with NASA on the Grand Asteroid Challenge, he wanted to put together a accelerated research program, and by accelerated we mean taking what you would originally consider as a PhD program or an introduction to a PhD program, and getting results within 8 weeks. So it's kind of like a hackathon, but vastly accelerated. And that would be taking planetary scale problems. So initially we were working on asteroid detection, and then we were so successful the first year that we were able to triple the problem definition in 2017, and we greatly increased the number of partners. The difference is that this is public and private. So NASA originally funded the first with ourselves, NVIDIA, putting in some pennies into the pot. But then we got covered by a lot more in the second year, and of course this is growing bigger and bigger and bigger. 2017 we also went to onto 2 continents, so we started Frontier Development Europe, and it's the European Space Agency that hosts that. And we're now looking at branching out into Asia Pacific. Primarily there is a workshop taking place in Singapore, which will include the Japanese, the Australian, the New Zealand, and the Korean Air Forces, or actually CARI, which is the Associated Research Institute, I believe it stands for. That's taking place towards the end. So this is basically just huge planetary scale problems, but essentially the kind of bread and butter that you guys live in. You know, planetary science across the board, whether that's helio, whether that's you know, exoplanets, and you can actually look onto Frontier Development Lab to find the results, because we publish everything. We open source all the results, and we publish papers. I believe there's been 22 separate projects so far, so it's a lot of fun. It's quite pressured for the actual researchers involved, but they're very well paid thanks to the funding from the private enterprise that's involved. We get some really good results, which you know is very good in this day and age, because things are always dramatically changing, so much so. I also work with the UN. I was at the AI for Good conference with many other people in Geneva back in May, and the UN Environment Office there took part in a special session that we had, that FDL was running for AI in space. And do look out if you have a look at David Jensen's LinkedIn. There's another article that's actually gone out today where the key message is, that investment is needed in what David and his colleagues consider to be the requirement of a digital ecosystem. So this is bringing everything, all of the data, excuse me, that we could possibly amalgamate, and bringing it in together, and of course having the data and the infrastructure to actually be able to handle it. And Earth observation features highly. ESA's current focus for Frontier Development Lab is based out of Esrin, which is the Earth Observation Centre. So it's the Sentinel and all of the older satellite constellations, plus all of these startups, because ESA's remit in Europe is to enable European startups, and there are very many starting to operate in the satellite, let's say, data analytics side. So that's very interesting, but also fast tracking again, because David Jensen started the AI in space session by saying that we literally had 10 years and that we needed to turn this around now. And this article is basically saying that these decisions and investments are needed in the next 1 year. So let's hope that there's some forward movement. Okay, so what does NVIDIA have to do with planetary science and everything that I've spoken about so far? So we focus on 3 things. Graphics, for the obvious reason that we started out in gaming, but we do a significant amount of work in both design. So if you think about designing buildings, architecture, etc., the visualization that's behind all of that, and also rendering. All of the Hollywood movies that win awards, basically using GPUs on the rendering side. In addition to graphics, there's HPC, high performance computing or supercomputing. This is a massive scaled challenge in itself, putting together all of the myriad of interconnects, servers, storage. Our data center business is huge, but also at the supercomputing stage, and what I mean by that is the national labs. Our GPUs are powering, the world's #1 at Oak Ridge, and a lot of the science that I don't know what access University of Florida has to the national labs, but obviously having that kind of capability, or for example, being awarded hundreds of hours on certain national lab computers is can be very rewarding, as well as produce some fairly epic results. And we do a significant amount of business in that. And then the other side of the third of our focuses is AI, and that is a massive field in itself. So when I say AI, I'm encompassing everything that we can think of with traditional machine learning, with natural language processing, and every tiny aspect. But here, if we just cut a dividing line between the training side, so the GPU acceleration, the massive parallel processing capability, and the inference side, or what we consider deploying at scale, deploying to billions of users. We do a lot of work on bringing down, so this is low precision, mixed precision. Even if folks are rethinking floating point itself to try and speed up the actual the time to inference, or the actual time to get that result, that insight from whatever the application is. And then of course there's the robotics side of AI, which I'll talk about in a little more detail. So from the HPC side, what you're looking at here, and the reason for the relevance of GPU, the graphics processing unit, is to be able to do both compute and visualization at the same time. So we have software called ParaView and Index, and I have just been given the nod to actually say if anybody actually wants some help in the visualization side of their large-scale simulations, then please just let me know, because I've got research that specialise in this. So this is 7 terabytes of data showing a supernova simulation that was actually run on blue waters. But with the software that we have harnessing the GPU side, we can actually do both the visualization, just to give you an idea. So for those of you who perhaps don't know what a GPU is, this is Titan RTX. This is one of our essentially close to, I would say consumer, except that it's a Titan grade. So it's our next best over consumer or gaming cards. RTX basically is the reference to our latest chip architecture, which is Turing. There are 4,608 cores on this. Our Tesla cards go up in excess of 5,000 processing cores. So that's 5,000 potential in parallel simultaneous operations that can be carried out. But we've also now introduced specifically on the Turing RTX cards, specific ray tracing cores. So these are dedicated cores for performing ray tracing, because of course the Turing card was actually brought with a focus on visualization, on graphics. In addition to the Tensor cores that were introduced on its predecessor, which is the Volta chip. And Tensor cores are specific cores that are enabled purely and simply to do the matrix accumulation, matrix multiplication and accumulation. That's pretty much the workhorse of artificial intelligence workloads, the driver when you're talking about backprop. So there are dedicated cores which again increase the time to insight. And I've just been speaking to the researchers at the Swiss AI Lab, when you're in a research facility, you're not necessarily wanting to get the fastest time to train, but of course it does make a considerable difference if you're taking 3 or 4 days to actually train something, and you can bring that down to a few hours. So just for those that aren't familiar with GPUs, this is as I said, the Titan RTX, and we have a whole range of GPUs, not just for the gamers who, you know, we basically established on a $1 billion gaming market. You know, the NVIDIA stands high because of our gamers. We're very proud of our gaming roots. But for researchers as well, the Titan is a great startup. Quadro is specifically designed for the visualization side, for the graphics side. But we have desk side, or we have servers, or on the end there, DGX2. It really depends on the capability. Our entire supercomputer in Santa Clara is made up of the last two there, DGX1 servers, but also DGX2. If you imagine a hotel minibar, that's the DGX2, which is capable of 2 petaflops of flops, floating point operations per second. It's pretty hefty in its capability. And it really depends on what you want to put together. And also, if you're just using single units, it depends on what kind of memory requirement that you actually need. Obviously, the larger, the greater the memory that we can stack in there, as well as the storage that we can stack into. Oops, had a little bit of feedback there. I hope that wasn't me. It's coming up with you, Julie. Can you go?
To stop this.
Oh, so
Yeah. Nope. It's off, but I need to get it out.
It's stopped now. Okay. Okay, all right, I'll carry on. Obviously, hardware means absolutely nothing without the software. So NVIDIA spends a massive amount of time, probably more time now on software than on hardware, because this is constant refactoring, constant improvements, constant optimization of over 40 separate libraries that cover, you know, as it says here, linear algebra, parallel processing, signals, deep learning, machine learning, visualization, a huge number of software libraries, because we're dealing with all of these individual, and actually this is just a selection of the genres that we're actually covering. Computational fluid dynamics and life sciences have a great number of what we call codes that have either been ported to GPU or are currently being ported to GPU. And all of these apps that we talk about, you know, there's 500 plus now, and that's growing every single day, are all available via this same platform. If you just sign up to developer.nvidia.com, you can access them. But we've even made that easier, and I'll get to it in a minute. So I'm kind of hoping that this will work, and I'm hoping that the volume won't be too loud. I don't know how. I might be able to switch it down on my own. Can you see the screen? I don't know if, I think maybe the volume's been turned. Okay, that's not too bad. Okay, so Phil Hume, that's my big brother. And this is his software. This is his Roadfrog software that he wrote back in 1980, I think it's 1984. So I've actually been in this game, you know, inverted commas, for a long, long time. And this is what we talk about when we say, I'm just going to pause this, otherwise. This is what we talk about when we mean 8-bit. And 8-bit is very, very simple. 8-bit for computational complexity is very, very simple. Just 1 second, I need to move this on a little bit. I'm kind of stuck now. 1 second. Okay, once we get into, next one. Once we get into things like 4K resolution, then the computational complexity of game environments grows significantly. Even, you know, to some extent with CPUs, it becomes intractable. But what you're looking at is the realm of today's reinforcement learning, or rather multi-agent reinforcement learning, where you are setting up virtual agents to learn how to play, in this case, real-time strategy games. So what you're looking at is StarCraft 2, and it is estimated that the amount of compute that DeepMind used to actually win against humans, so this is the AI beating a human player, actually multiple human players. The estimated machine cost to train this system was about $26 million. You could also probably say that DeepMind's, you know, researchers cost that same amount, because, you know, there were hundreds of, you know, folks involved, and they're quite well paid. But this is the realm that they play in, and they use these virtual environments for several reasons. Even though you need huge computational costs behind to get to this level of understanding. The simulation itself, once set up, is of course, you know, no cost or negligible cost. But you can also use the parallel processing capability and also the parallel action. When you take something like, so StarCraft, I believe, has 300 possible actions. And if you put that in comparison with Atari, that has about 10 possible actions. When you take a simple 84 by 84 pixel screen and then compute the number of possibilities, you know, within that problem space, it's getting into the hundreds of millions. So you need you know, exceptional computation, but you need, and you absolutely have to harness the parallel nature of GPU accelerated processing. And reinforcement learning comes into play a lot with robotics, and we do a lot of research. We have Dieter Fox, who runs the robotics lab in Seattle. We also have Sanya Fiddler, who runs a lab in Toronto. But specifically in the Seattle office, we do a lot, both on the industry side as well as testing state of the art, for example, you know, with different arms, robotic arms, or full, you know, dual armed, as you can see here. You can also interject into these simulated environments and start playing with things like evolutionary strategies within these simulated environments. In fact, you basically, you know, it's the only way that you can put this into practice, or rather put the theory into practice. And a great paper is Poet by the Uber Lab, but actually Jeff Clune, who's University of Wisconsin. And this is the way to massively increase the not only the search space that can be searched, but the area of the search space. When you think about traditional backprop techniques, for example, you don't really search the entire space. So you will converge to a solution, but a lot quicker had you had this capability. So a lot of this, I'm a big fan of these, you know, ESA, evolutionary strategies, or genetic algorithms. There's excuse me, there's lots of different terminology that's used. It's essentially just having, excuse me a minute, I'm just having a drink. Being able to widen the search space depending on the application. And of course, you need these simulated environments. And the same thing with the free energy principle, actually, with Carl Friston, originally of, actually, he still is at UCI. And it basically comes down to, as it says here, the difference between the states you expect to be in, the states that your sensors tell you that you're in. It has a lot to do with the robotics side of it. but using things like genetic algorithms helps to work through that entire mathematical space. And I like to include this because at this stage, a lot of people tend to forget that what we're trying to do is augment ourselves, is augment the skills that we already have. So it's, you know, it is very, very much a case of making your jobs easier. Not automating everything that you do, but perhaps adding a little value add to something that you're currently doing now. And this is the kind of thing that happens in Frontier Development Lab, where we'll take a certain problem that you know has a particular pain point, and we'll try and fix it by putting almost, you know, in a modular way some form of artificial intelligence into the solution to help it. But I like to make a point of saying that this is not about, you know, just taking everything that you do and automating it. It's about helping you. So getting back into the robotics side of things, this is obviously very, very. I believe this is the future. It's going to be, you know, automation at different degrees, but by many different kinds of autonomous machine, and that could be delivery vehicles, you know, bringing pizzas. It could be the next stage of curiosity on Mars. It could be certain aspects within spacecraft. It could be autonomous vehicles, you know, even down at say CubeSat size, that are actually formed trains to actually go and do exploration at much lower cost than today's spacecraft. But all of these combined, and humans, all revolve in this in this, you know, circuitous loop, where we think about something, we act on it, or you know, we use the term actuators with robots. This alters the environment. We then look around, we perceive, we hear. You know, we have our 5 senses, and we're only really using touch. We're not really using smell in robotics at the moment, or taste. So it's really just audio, sound, and touch. And we do that, and then we think about it again and make an action which changes the environment. And this goes on and on and on. And for those of you not familiar, this is the mathematical side, because all of that goes into markov decision processes, where you have an agent that performs some kind of action that has an effect on the environment, and that they then get a reward for that. So that reward comes back to the agent, but at the same time, the state of the environment changes, so the agent is now in a different environment, and this goes on and on and on. And you can define this as they do in a 5-tuple. But the objective with reinforcement learning, which is essentially just supervised learning with dynamic programming, which is the Bellman equation, essentially, is to act optimally, and put mathematically, it's to maximize the expected long-term discounted reward, or the actual value of the task in hand. But essentially, it's just to make the most optimal decision, if you take that as an overarching. For example, giving Curiosity on Mars some high-level instruction, you know, go from A to B, and it can figure out the most optimal way of going from A to B. We don't have to do all that calculation. It can do that itself, because it's capable of bringing in that slight autonomy. Everything by itself, but to help it make that decision. So the Bellman principle, as you know, hopefully everybody knows, maximum expected return. This is the dynamic programming part of reinforcement learning, which enables or helps enable the self-play aspect, which is where you know, various widely popular challenges were actually met, such as Go. A lot of it is self-play. A lot of the strategic wins in things like StarCraft 2 games and Dota 2 games, these strategy games, is because of self-play, where you're able to take multiple agents and they're all playing against each other with different parameters. And a lot of researchers now, when they're doing training, will try to find lots and lots of different hyperparameters and have one model train against another model and then get the most optimal of those. And you know, this is a lot of the workload in training right now. But again, getting back to the simulation side, what you're looking at here is use of our Isaac platform. So this is actually being upgraded right now. So it currently runs on the Unity or Unreal Engine background. But what you're looking at is thousands, you know, harnessing the parallel capability of the GPU, because it has thousands of cores. Thousands of agents who, it should reset in a minute, but from scratch, they don't know how to stand up or move around or anything, but they've been set the task. Let me just run that back again. If you notice, right, you know, they do it faster than I can actually talk. It starts from lying flat, and then they have to learn how to stand up, how to walk. And here it's learning active behaviors of what happens when you're running into one another. So that capability is only possible with the parallel processing capability in simulation. As you can imagine, having, you know, many PR2 robots running around like this would be just ridiculously expensive. So having that simulation capability is really, really important. And here, for example, is what we've done is we're able to, of course, you can make this environment whatever you want. Here we've made it into a cute looking nursery type environment. It could be the kind of environment on Mars. It could be the kind of environment that you need to train an astronaut, for example. You can make the environment whatever you want, but here what we're looking at is a screenshot from my colleague Hamad's headset. So he's got a VR headset on, and he's actually wearing haptics, and he's literally playing dominoes with this virtual robot. And the robot is actually learning with reinforcement learning, with a policy and a value network. So every move that it's watched Hamad make, it's assessing and then working on the same mode. Obviously, this is just a very trivial game of dominoes, but it's the concept that we're trying to show. So within the actual simulated environment, you can inject, you know, all kinds of artificial intelligence in the form of training, whether it's reinforcement learning or supervised learning or semi-supervised learning, but within the actual environment. So it's actually very, very exciting, especially when you bring in haptics. And of course, what happens is once you've got that virtual robot trained to a desired accuracy, you then just take the weight and port them into a real robot. And we actually took this robot to I forget, I think it was one of the SIGGRAPH conferences, and there was actually a real PR2 playing dominoes with users, so it was quite fun. So we have this platform, we call it Isaac, and the sim version, so the simulator version, is fully open and available to anyone via that link. There is also a gym version that is coming soon, and that will incorporate all kinds of reinforcement learning models and capabilities. And it's actually taken a little bit longer than we thought to release the actual open, the Isaac gym part. Excuse me. Because we're incorporating something that we call Omniverse, which is essentially our own virtual world, our own virtual environment, that brings in physics. I don't know if anybody's familiar with physics. That's the physics engine behind all of our visualizations in physics work. So you can set gravity to whatever you want it to be, for example. And we also have various robots that we work with in-house in Santa Clara and in the robotics offices, and you can see them there. Kaya runs on Nano. It's actually just a 3D printed sort of palm of your hand sized unit. And then Carter is a delivery vehicle that runs around our headquarters in Endeavour, being trained on lots of things. And then we do, we scale up to multiple Xavier based. Xavier is a 30 watts or 30 tops, I think it is, trillion operations per second. So that's basically open to anyone who wants to use it. We have a lot of different work that we do internally with our research arm. One of them is using, obviously a lot of robots these days use fisheye lenses. Excuse me a minute. Just taking it. And fisheye lenses, we have a lot of software that we just kind of throw out to the world, where you can convert the fisheye to the best perspective that you actually need. Here it's just removing radial distortion, and all of this kind of software gets pushed out to developer.nvidia.com, which is where everything is that you actually need. Here is actually some work from our Seattle office, where this in simulation is a very popular part fault operation, but that's my colleague Brian, where he's actually perturbing the results of the arm, balancing it to incorporate, but also to demonstrate the fact that negative feedback, which is very, very important, especially for safety critical and mission critical. So this is just a demonstration of some of the things that they play around with. Part pole, as I said, is one of those demos that a lot of people sort of cut their teeth on for reinforcement learning. And this is Stuart Anderson. Can you hear this all right?
Every day I get to work with robots and teach them to do things that are agile and flexible.
So going back to the previous demo, if I can, this again is really important work for when you're bridging the divide, and we come up with this when you're bridging the divide between simulated and environments and reality. And again, the negative feedback here is really crucial for testing that. Because it's crossing that bridge, and we do a lot of work with self-driving cars for sim to real and bridging, and we've actually put out papers for that as well. So just let me run straight through. This was just published. Let me just turn that music down a little bit. I think this was published at ICRA today. This is out of one of our other labs. But as I was talking about, closing that sim to real transfer loop, and you can go to that paper to actually have a look at that in a little bit more detail. So all of this, of course, needs to be backed up by the actual hardware, and we call this the embedded side AGX, A standing for autonomy, and it's across a whole family because this same hardware drives a lot of the healthcare work that we do, as well as smart cities. So think of things like intelligent video analytics, intelligent CCTV cameras, things like that. As well as all of the self-driving car work that we do. And that is, of course, the ultimate problem. If you can solve self-driving cars, then you've solved all the other problems that run downhill from that. But it's all via the embedded GPUs that we say here. And a big part of that was actually open source. So if you go to NVIDIA.org, the deep learning accelerator side was open source. I think this was about 18 months ago, possibly potentially even longer than that. So you can literally just take those entire tech specs and work with it on the DLI side, and integrate them if you're actually doing your own micro controllers. And of course, the ultimate edge device, as we call it, or the ultimate robot, with slightly less hassle because we're deliberately avoiding things here with self-driving cars. It's the environment that it causes the major complexity. This incorporates everything that we do. But one thing that we learned is to get to that level of autonomy, with the simulation required and with the training required, we literally had to re-engineer hardware. And this is why we came up with DGX2. And not only DGX2, but pods and pods of DGXs. What we call a pod is 6 of those square units with the storage and CPU and interconnect next to it. And our supercomputer is made up of we're approaching 2,500 nodes now of these minibar sized. What we call DGX2, simply because of the computational scale required for all of our self-driving car work and all of the other work with all of our clients around the world, for example. And this just gives you an indication of exactly what kind of labeling is needed. And for a single car, we estimate 10 DGX1s, which is actually the servers. There's 16 GPUs in each of these square DGX2 pods that we look at. And you need 100, so you need 50 of those per car, essentially, to do all the computation required, which is fairly staggering. This is DGX2. There's 2 sleighs of 8 Volta GPUs with all of the switch and interconnect and the engineering completely re-engineered for storage, and 2 Xeon Platinum CPUs or GPUs work alongside. So it's the capability that's really interesting. But this is interesting for the simulation side. Clearly, you are more interested in spacecraft as opposed to things on the road, but we work with self-driving cars, just like breakthroughs that happen from space will eventually come down to Earth. For folks to use it, we can go the other end. We can go from Earth into space. So Drive Constellation is what literally drives the virtual reality simulator side of simulating and training and creating data to retrain self-driving cars, and that again is powered by GPUs. So the VR simulation should be something that you're considering when you're trying to bring all of the different parts together. We call this entire side of the business Drive, AV for autonomous vehicle. But when you just think of all of the different parts that go into trying to train a car, braking and steering and other traffic, and it's just a few of them. We call this safety force field because, of course, safety and planning is a massive part of this. Is the ultimate critical control mission for us here on Earth. there are various other aspects when you start getting into space. So we take a four-pronged approach for validation. Resim, so it's simulating and resim, so regression testing on the actual real data. Software in the loop simulation is regression testing on synthetic data. And then you've got hardware in the loop simulation where you're using real-time data and then coupled with the actual fleets of cars that are actually going onto the ground. So, you know, everything that we learn, if it's of interest, is available in our ongoing safety report. And it is a continually, you know, learning environment. We're learning this as we go. But it's all very, very relevant for everything else in your space, which is things like, you know, all of these things down the left-hand side are the potential uses for AI within the, let's say, life sciences side or the planetary sciences side, detection, planning, acceleration, simulation. And I'm not going to go through all of these, but just to give you a couple of ideas. We know about monitoring environmental change. We know about the Earth observation side. That's what's going on in Frascati right now. Is trying to figure out. And there's a lot of work going on with ice cover. Actually, there's been a lot of papers and work covered over the first couple of days, the Tuesday, the Monday and the Tuesday this week. But also route planning, you know, optimizing, not only getting resources to certain places, but evacuation routes, for example, can be really interesting. When you use reinforcement learning, especially when you stop learning evolutionary tactics as well. And the same goes for autonomous agents, you know, off-world as well as on-world. For either the sensors, having intelligent sensors, or that helping the actual agent itself to make decisions. There's various work that we're doing right now for NWP, numerical weather prediction. But there's also things like using in-painting. So this is where a system is being trained on historical data and is able to in-paint, to literally fill in the gaps, so to speak. And here it's work that we were doing with NASA on those observations to enhance what we actually have. Nowcasting as opposed to forecasting. You can have AI powering this with the prediction side. I don't work specifically on this, but I've got colleagues who do. David Hall is NCAR. He now works with us primarily on this kind of thing. This is really interesting as well. Obviously, this is waving the UK flag. Take a look at Deep Earth observation. So the photo that you're looking at is of Goonhilly Earth Station, which is an old BT site. So it has incredible transatlantic and, in fact, global links for communication, both undersea and fibre optic. But it also hosts many radio telescopes. The site is now privately owned by, and is known as the Goonhilly Earth Station. But they are setting up a deep space network, and they've also put together the Deep Earth observation website because they are harnessing the GPU capability of DGX. DGX1, so these servers of 8 GPUs. So that's interesting work, and I can put you in touch with Ian Jones, who runs Goonhilly. It's an interesting place, especially for the fact that they have prime coverage for hence the Deep Space Network. I think it's 24-hour coverage for Luna as well as, I forget the other one, but I can put you in touch with them. They're really interesting. This is the architecture of Maxar Technologies, who have since bought Digital Globe, their Deep Core SDK. And every single part of this was actually built harness GPU acceleration. So from the storage side to the processing and the data ingest. And it's really important to speed everything up when you're getting that, more for an Earth observation side than planetary. There's also lots of work. This is similar to work that was done at FDL. This summer actually. I get a little bit confused. We're clocking over 20 separate projects. That some of them are actually, the majority of them are ongoing. But this is work with Goddard, where you're able to harness AI to predict, but also enhance. This is working with the Celeb A data set, so hence the uncanny valley human faces that you're looking at, but it's actually generative adversarial networks, which is looking through the entire mathematical distribution of what would constitute the optimal face. And of course, you can put this to work in many, many different areas, including here at Hawke. This is work that a colleague of mine did with a couple of interns with the High Altitude Water Terrain Observatory, and where they were using the GAM. My colleague is Gus, Michael Gus. They were using GAMs to predict the actual cosmic rays. And so there's a lot of HEP work, high energy physics, where this is, I'd say state of the art, but it's kind of like, it's almost fringe because people haven't really understood or don't yet understand the capability of it. But it really should be now, because we're starting to, we are literally going to be, underwater with the amount of data that's coming in. The square kilometre is exabytes a day. I mean, that's just unbelievable amount of data. Once the LHC goes up to high luminosity, they have to, they're working. There's 10 to 20 separate projects that we're working on with CERN right now, just to prepare for that 10x increase in data volume once it comes online. And ITER, of course, is ongoing, but is yet another just source of huge amounts of data that we need to be able to cope with. And we're working with a lot of this. But so what we're seeing is this convergence of high performance computing, AI. So it's the scientific work that you're doing, but at much more massive scales, on top of the 40 plus years of the first principles theory and the modeling that you know. You can also bring in AI, and we're quite happy to work with on anything that you wanted to scale. FDL takes, these small problems and brings it to fruition, brings it, incorporating mentors that haven't perhaps yet used AI. In fact, the key thing about FDL is it's cross collaboration. It's the physical scientists with the AI scientists, with the computer scientists. So whatever the science is, the physical scientist does not have to become a computer scientist overnight. They can just sit in a room for 8 weeks and hash out a solution to a problem. And of course, the computer scientist is therefore going to learn about their science, about the particular problem that you're working on. So it's that cross collaboration, which is really, really powerful. At large scale problems, for example, like climate change, I personally want to see a lot more of this work with climate change, and hence the UN. But we see some pretty amazing Gordon Bell winning, award-winning results, and this is work that we're doing with LIGO. Daniel George actually just won a NVIDIA fellowship with us, so he's been doing a bit of an intern, but he won a £50,000 award for this work with the gravitational waves, where it's actually the multi-messenger astrophysics side of it, that's the GPU acceleration has allowed it almost to be real, or at least quick enough to be able to move the telescopes, and the actual inference side much quicker. Thousands of times quicker. That's some really interesting work. This is work by Schneider, and Brant's the supervisor. Evan wrote the Cholla hydrodynamics code for her PhD thesis. Essentially, this allows us with index and paraview to assess outpassing of the actual flow of galactic winds. And although it looks very, very pretty, it's also mathematically correct. So that's really cool work as well. So all of that and details on that, including the paraview and the index, are accessible by what we call NGC, and this is the GPU cloud, and it's probably quite a confusing name, but it's essentially just a really great UI user interface that you can pull down containerized software, including paraview and index, should you wish to use it. It also includes a lot of other deep learning, machine learning, etc. Work. And the reason that we've started to use containerized software so much is simply for ease and to make it much quicker. Literally do a pull command to pull down a container with the entire environment mapped, and that means that multi-users can use the same equipment, and you don't lose anything with you can literally share the container that you were working on. So it really does help on reproducibility as well, and that's across any hardware that you could be using. And you simply click for what data you want to use. You click for what models. NGC is really good. Take a look at it. It includes lots of examples. We have a model zoo on there, whether it's, as I said, deep learning, machine learning, or specifically for inference or whatever. There's many different ways, and it's completely free. You just sign up to be able to use it. You can also put your own custom containerized software in there as well, and literally watch as the training actually takes place, or aboard the job should you need to. So there's 5 main routes to harness GPU computing. You don't have to just rewrite all your code. OpenACC has been around for many, many years now, for the simple fact that there is many years worth of legacy code that's out there, where you can simply just use pragmas to put around the certain parts of the serial code that you can parallelize, for example. There's many routes into it, and I certainly can't go into exactly the how and why, otherwise we'd be here for weeks, but not just an hour. And data science is, of course, a whole field in itself. But as I said, we've put together software to help. This, as it says, is reimagining the entire workflow, both for the preparation side and the wrangling, the ingest of data, to the actual model training and the actual visualization. We call this rapid, completely open source. There's a ton more information that I could tell you. I'd love to tell you NLP, but I don't have the time. It's potentially not that relevant for you. This is where you go to pull any of our software. All our software is completely free and constantly changing. Hence the reason for using NGC now and having containers. We just hosted Onyx. Onyx is the Open Neural Network Exchange, and it's about standardizing the actual software, or rather the frameworks that are used, so that you can, no matter how you train the system, you can push it to, for inference, for the actual deployment at scale time. We just hosted that endeavor a couple of weeks ago now, so we work closely on standardizing with, even with our competitors. Should you not have DGX or GPUs with you, then all of our GPUs are actually in the cloud. Even our Turing cards, what we call T4, which are small inference GPUs, they're available on Amazon and Google now, I believe. So across the board, every cloud provider has got our GPUs. And that NGC UI that I mentioned enables you to what we call burst out to the cloud, should you need it. When it comes around to paper deadlines, there's always a huge spike in the need for compute, so it's good to be able to burst out to the cloud should you need it. So that's available there. And this is our little nano. You can buy these online. It's it's got a Maxwell card, which is the reason that we can provide it just for $99. It's a great way to actually learn to harness GPUs when you're just playing around with a prototype idea. So you can just buy those online. But we also provide a ton of different things that we call Jetbook, and it's nano based. So this is a full open source community that's providing lots of different sort of recipes, and here's something that I did, here's something that I did, and folks get together and talk about it. And even 3D printing designs for certain. So you can go online there to take a further look. This is just to give you an idea of what can be done with a single nano, $99. So here it's capable of processing 8 separate real-time video streams and performing object detection. If you use Xavier, you can then ramp up to 64 separate screens. This is what we call smart cities. It's an intelligent video analytics side. But Nano is very, very powerful, even though it's $99 and in the palm of your hand stuff. So all of the software that's specifically for embedded is what we call Jetpack. Again, that's completely available online. You can just download whatever you need. There's a forum as well should you need any help with anything. Fully integrates with ROS and all of the other side, but with the advantage of GPU video codec and all the perception that we've done. It's very comprehensive. You can get everything that you need at that site. In fact, the entire ecosystem is run online because we literally don't have enough people to scale the entire community of what we call embedded, robotics, etc. And the make community. But we do have free teaching kits, so you can just go to that website and download the teaching kit for robotics. And that's literally, entire sort of curriculum that we've worked with. So that was a ton of information. There's a lot more available online. I don't know if you're familiar with Jupyter notebooks, but they enable you to code directly on GPUs. The cost if you're accessing GPUs in the cloud, of course. So some of the actual classes aren't free, but they do cover pretty much everything that you can think of. Although we don't currently have anything for planetary science, and I'm working on that. So if you do need something, do let me know. And you can go online to DLI to learn a bit more. And if you are in the neighbourhood, we actually have a conference in DC, November 4 to 6. And I would advise if you're in the neighbourhood to go and have a look there at what people are doing, both defence and federal scale, but also for all of our robotics side will be there, and lots to learn. So that's it. Thank you very much. And, let me just flick off and let me take a look at the chat screen.
Thank you very much. So
I wasn't looking at the time very well, actually.
yes, I was trying to signal you. So.
Okay, all right.
You're
I
fine.
was on full screen, so I couldn't see
No
that.
problem, no problem. So does anybody have questions in the room or online? Online, please use the chat box.
You can don't hesitate to contact me if you let me just flick.
So you're doing a lot of really amazing things. Are your platforms going into CubeSats?
Yeah, so we currently have, just bear with me a second, I am stuck with, oh there you go, was unable to do the stop sharing. Yeah, so Jetson is the name that we call our embedded range, and the predecessor to Xavier is called TX2, and it's capable of about 1.5 teraflops, so trillion floating point operations per second, at anywhere between 5 and 10 watts, depending on the actual workload. And there's been, because it's been around now for I think 2.5, 3 years, there's a number of startups that have been doing some pretty cool stuff with it. So one startup has been doing hyperspectral imaging. However, it's the actual unit is positioned on the ISS, so it's actually protected. Right now, there's only one startup that I know of that has Jetson in orbit, and that's offering internet TV, a company called Hyber. But there are many, many others either waiting for launch windows or still doing testing. And we have several partners that are actually working on RadHard for several contracts with NASA. ESA and NASA are both testing Xavier for craft.
We have a question from our online audience. Lee asks, how does the GPU compare with Google's TPU or in-memory computing solutions?
Okay, so TPU is dedicated for use on, if you're using TensorFlow, then that's what they're gearing TPUs for. It's in certain work cases, it's actually more performant than GPUs. You are limited to using TensorFlow only, whereas our GPUs will work with any framework. But we work very closely with Google. It's an excellent piece of kit. They're also one of about 70 other players in this market that are designing chips specifically to do that matrix multiplication and accumulate, which is, as I said, their workhorse, dedicated mathematical operations. So yeah, they're great. We love TPUs.
More questions? Well, very cool. I want to thank you very much for taking the time to talk to us.
My pleasure.
And we're looking
Anything that I can help with. You've got my email.
Yeah, we're looking forward to working with you in class. And
yeah, absolutely. Sorry I missed that first set, but too much going on with travel, etc.
Yeah, well, I know how that goes. But there's going to be a lot of interaction between new space and science and engineering, and I'm looking forward to opening up some interesting possibilities.
Absolutely, especially with the asteroid side and Lunar. Take a look at the Frontier Development Lab page for the results.
Okay.
Not only from this summer, but from previous years. There's some really great papers, and a lot of it is probably just to allay fears, from senior execs that are still perhaps a little bit worried about putting some degree of autonomy in it. But there's some good work there, and I look forward to working with you closer.
Okay, well, thank you very much.
Okay, all right. Thanks for listening, everyone.